And we have coming up Sam Power from Cambridge. He's a fourth year PhD student interested in Bayesian statistics, as all of us, particularly Monte Carlo methods. And today he'll be talking about accelerated sampling on discrete spaces with non-reversible Markov processes.
All right, I'm going to try share. All right, you can see me?
Yep, I can see you.
Can you see me writing? Is that all working? Okay.
Yep, hi.
Excellent.
Yep.
Excellent. Okay, let's get started then. So hi everyone. Thanks very much to the organizers for setting this up. You know, it's a strange time for everyone, so to actually be able to organize something as elaborate as this is very impressive. And thanks very much to everyone for coming along. So I'm going to talk about some work I've done with Jacob Goldman here on non-reversible MTMC on discrete spaces. And we sort of, you know, finished up a first draft of this in December, but we're sort of working on some developments. Yeah, and it's sort of going to have some links to Alex's talk later this afternoon. So it's sort of useful to contextualize it in terms of that. Yeah, and this is some work I'm pretty enthusiastic about. So please do, you know, engage and ask questions and so on. Like I'd be really happy to hear what people think. Okay, great. So to get started, what I am interested in doing today is sampling from a probability distribution, pi of x, where the key thing, I guess, is that x is going to be a discrete space today. And this is sort of not the setting on which most work has been done. And so, okay, what I'm interested in is drawing approximate samples from pi, say, and I'm going to assume I'm in a situation where drawing exact samples is not really an option because I'm in a high dimensional state space that doesn't have enough structure to make that super easy for myself. So I can't do exact sampling, so I'm going to use an iterative method, and the sort of standard iterative method is what's called Markov chain Monte Carlo, or MCMC is what I'll usually abbreviate that to. There are some other ways of approaching sampling here, like SMC samplers and so on, but it's sort of a separate mechanism. So what I'm really looking at is trying to design methods for exploring a discrete state space so that I target some invariant measure pi. Okay. And so what we wanted to do was get a handle on how we should design dynamics for sampling properly. You know, beyond just proposing a random neighbor and seeing whether to go there or not. What can we do something a bit smarter? And okay, so the high level questions are, what properties of a target can we exploit that will make this easier for us? You know, you can't do anything in a complete black box setting. So what intuition can we build for these tasks under certain structural assumptions? And in particular, can we get something from the continuous world, even though we're doing discrete sampling? And I'll sort of, explain that. Some sort of rules of the game, I guess, is that I want an algorithm which gives me asymptotically exact samples. You know, if I keep iterating this Markov chain that I generate over time, I want to know that they are getting closer and closer in law to this pi of x. And the reason for this is manifold, but I think the most important one for me is that it's modular. So this means if I have some model that has, you know, discrete and continuous parts, I want to be able to do updates on the discrete part so that if I look at what's happening at the whole system, I'm getting the right invariant measure there as well. And what tends to be the case with these Markov chain-based methods is that if you start making mistakes in one part of the system and you're not exact there, it's not clear how those errors propagate around the rest. And so there's a real incentive to be exact in some limit. So that's what we're sort of setting as our rules, right? Okay, so we'll move on to the next one. Right, so what is very well developed by now is how to do sampling in continuous spaces. Essentially because if you have gradient information from your target, you know, if you have that your log probability pi of x is differentiable, then a lot of stuff is available to you, right? At a very basic level, it tells you what direction you should move in if you want to find a high probability region. It's very easy to see how that would be useful, right? And so I would say the vast majority of the algorithms that are used for sampling on continuous spaces, which sort of scale well to difficult problems, are based on some sort of continuous time process. So, you know, perhaps the first thing to think of would be an ordinary differential equation. So how can I follow the flow of an ODE around my space to explore properly, right? And this is the basis of Hamiltonian Monte Carlo, which is really widely used and scales well to high dimensional problems in general. What is sort of mathematically a bit more work in some ways and simpler in others is to use stochastic differential equations, which is somehow a more natural fit if you're doing random exploration anyways. Right, so you have algorithms like Langevin Monte Carlo, of which there's actually two. Essentially, one of them is gradient descent, and then you add on noise at a certain scale. And then there's what's called underdamped or kinetic Langevin, where it's kind of like a momentum-based method, right? Where you have a position and a velocity, and you use them to wheel around the space. Some more recent developments would be stuff like piecewise deterministic Markov processes. And I suspect this is what Alex is going to be talking about later today. So stuff like the bouncy particle sampler or the zigzag process. So you might not be familiar with these. I certainly wasn't until a couple of years ago. Here, what you have is a particle that follows the flow of an ODE and then jumps, right? So there's sort of a bit more to it. But again, to find regions of high probability, you will essentially be following the gradients of your probability measure in some way. You can also do more elaborate stuff. So if you want to use jump diffusions or Levy SDEs, it is actually possible to do this. It's pretty rare because it's a lot more effort mathematically to get it working, but it does exist and it sort of is somewhat useful, but definitely not as well developed. And okay, so what we were thinking was, can we build samplers on discrete spaces using this as motivation? Does this actually help us? Okay, so I'll talk now about why I'm interested in discrete sampling. And so at a high level, what struck me about this problem was that there aren't really generic solutions for discrete sampling which are good. So there are solutions which will work in principle, but the extent to which they stay working well in practice as problems get more and more complex is actually not so clear. And so actually at a motivation level for us, that's kind of what we wanted to work out was, can we make this work generally? But at the practical level, there's plenty of reasons to be doing discrete sampling. So I come mostly from a statistical background. And so you have problems there like variable selection. So this would be, you're doing regression and you want to figure out which variables are significant. And so essentially there you have some sort of inclusion variable, where sort of, Zi is equal to 1 if you think that the ith variable is relevant for the regression at hand, and it's 0 if not, right? So there's a sort of discrete nature there. Subset selection, so this is kind of more broad, but things like, selecting a bag of items from a range of things and you want some diversity amongst the items and so on. So if you've heard of things like determinal point processes or submodular point processes, these fall into that category as well. So to be clear here, the discrete space is something like 0, 1 to the n most of the time. You can have problems based on permutations, right? So the symmetric group, where you want to do like a ranking or a matching, or there's certain sorts of independence testing things you can do that are based on, permuting data sets and seeing how well they align. And so in this case, you have, you have a discrete structure and you have some sort of group acting on it. You also have applications in cryptography where, so for lattice-based cryptography in particular, sort of the way things are encoded involves these discrete Gaussian measures. And so here your state space is something like Z to the D. Depending on your background, you might also be familiar with statistical physics problems, which tend to involve, at least some sort of spatial discreteness, but also often in the state space itself. You'll have discreteness. So spin systems like the Ising model is probably what most people would be familiar with, but you also have Potts models and other more elaborate things. So for an Ising model, you would have a spin of plus or minus 1 at every site. You also have things like polymers, which are a bit more effort to explain, and things like lattice gauge theory, which are, again, sort of more advanced physics models. But at the end of the day, it's, you have some spatial lattice, and at each site, you have some variable which takes value in a discrete set. But yeah, so for us, the personal motivation was that it seems like a sort of fundamental task. It's, it's a very simple problem to state. How can we do it well? And that there's this sort of more general thing I've seen with different areas of research, where I guess you first solve the problem for differentiable structures on RD in Euclidean space, and then you say, okay, can I make this work on manifolds? Does the same information is it sufficient to define a good algorithm? So you sort of get more high tech, more geometric from there. And then afterwards you say, okay, well, what if I strip all the structure away, right? And I try solve things on graphs now. And this is something you sort of see with the neural nets literature, right? Where you have these highly structured equivariant networks and so on for doing imaging on 3D shapes and so on. And then at the other end of the spectrum, you have graph neural networks, which are, you really only have a very basic combinatorial structure on the space. So we were trying to sort of a bit inspired by that, trying to strip down sampling to its simplest case. What can we do? What can we achieve with this? Okay, so the basic approaches to discrete sampling that exist in the literature already, you have things like Gibbs sampling. So, oh, sorry, my thing's run out of battery. So Gibbs sampling is something that applies in very specific models where you have many variables, you fix all but one of them, and then you update that remaining variable conditional on the others. And in a lot of models, that's sort of very straightforward to do. But it tends to mix as well as the model dictates. There's not really much freedom there, okay? If the model is highly correlated, it will be difficult to make moves around the space. Now you also have things like random walk and independent Metropolis-Hastings problems, where you propose a move to a new point in the space, and then you accept or reject that move depending on sort of the ratio of probabilities of those spaces. And again, these are hard to design well in some, and they're often pretty uninformed proposals. You're just picking a random neighbor and seeing if it's better or not, which is not a great strategy in some ways. And then in certain models, there are very specific constructions you can make which use some symmetry property to make life easier for you. And this does not really generalize especially well, but it's in some models it's an option, in others it's not, and it's not really satisfying from a broad theory point of view. And so we wanted to build something general purpose. And another comment I wanted to make is that in some situations you have a discrete space which looks like RD more or less, things like lattices where you can sensibly embed them in Euclidean space. And you can use that as a strategy to say, okay, I'll take some continuous space algorithm and then apply it to this embedding. This can work well, but I think it's not really the right strategy in some way. It's a practical one, certainly, but from the sort of ideal algorithm, you really want to use the structure of the model itself rather than shoehorning it into some other setting. So we're trying to use the intrinsic structure of the space to design algorithms. Okay, so our goals. Exploit generic model features. So, you can't do anything without some structure, so we're going to pick a structure and roll with it. We want something that's robust to changes in model details. So we don't want something which works very well when the model has a lot of symmetries, but completely breaks down as soon as you add in some extra terms, right? We want something that's robust in the sense that you can change the algorithm a small amount and it will continue to work well. We want something that's easy to tune. Now, on discrete spaces, this is usually not too hard compared to continuous spaces. It's sort of rare that you actually have a step size or anything like this. And of course, we want something that converges quickly, because at the end of the day, that's why we're doing the algorithm. So we want to design a Markov chain which decorrelates quickly and ends up at an approximate sample from pi as best possible. Okay, so that's setting the scene, right? We want to build a discrete sample we can use pretty generally. Great. So the approach we're going to take is sort of in keeping with what is suggested by the continuous state space case, which is that we would like to construct some continuous time Markov process which samples from pi. So in the case of Hamiltonian Monte Carlo, Langevin Monte Carlo, this is what we're doing. We're taking some continuous time process which does what we'd like, and then we're approximating it if we have to, okay? And you can sort of build something out of that. And so the reasonable question is, if I'm on a discrete space, what is an ODE, right? What is an SDE? What is a PDMP? How do I interpret these things if I'm just hopping around on a graph? And what is essentially true is that if you look at a Markov process on a graph, the only thing it can do is at its current location, wait for a certain amount of time, and then jump to a neighbor, okay? And so in that respect, there is no distinction between an ODE and SDE or otherwise. All you are doing is waiting and then moving. Even the sort of deterministic ODE type thing, you are still waiting a random amount of time. And so what you can say is that, okay, actually anything I do will end up being a Markov jump process. So that is sort of the right level of generality at which to work. And so we will try to construct a Markov jump process which has the right invariant measure. So I think that's what I wanted to say there. Yes, so I should emphasize, this approach here, I've just sort of asserted that it's a good thing to do. What is also seen to be true is that it is practically a useful thing to do, in that the practical algorithms people are using can be viewed in this way. Now, they're not always built in this way a priori, but it's almost always possible to do that. Okay, so moving on, what is a Markov jump process? Again, it's not a super intense thing to have to work out, but maybe we haven't seen it recently. So essentially what you have is, you're at some position X, you have, Y, which is a neighbor on the graph or the discrete space you're considering. And associated to that, you have some jump rate, which is a non-negative number. So it doesn't have to be between 0 and 1. It's sort of like an intensity, or like you kind of have a clock on that edge, which goes off at some rate. Okay, so yeah, you specify a jump rate. You have a total jump rate out of the state. So this capital lambda of X is sort of how much the chain wants to leave its current state and go somewhere else. And so the way you simulate this is essentially you say, I stay at my current location for an exponential amount of time, right? Which is something we can simulate easily. And then we jump to a neighbor Y with sort of probability proportional to the jump rate, okay? And the one key thing here, I would say, is that this is something you can simulate exactly in continuous time. So there's no discretization needed because you're already on a discrete space, and somehow that makes life much easier for you. Okay, so there you go. That's a Markov jump process. Yeah, a useful thing to highlight here is that in one sort of computational step, you always move. Okay, so for Metropolis Hastings type moves, you will propose a move to a different location, and then you will go there or not, according to some probability. In this case, you always move, but you wait a random amount of time, but you don't have to wait that amount of time in real life, okay? So that's a sort of nice thing, particularly for really frustrated systems where you get stuck in modes and so on. Okay, nice. So let's just speed up a little bit. So, what we want to do is derive a Markov jump process which has pi as an invariant measure. One easy way to work this is to make the Markov process be in what's called detailed balance with respect to pi, or be reversible. And so this is just an algebraic condition. As we see here, it's something which we can actually force to be true very easily by saying, okay, for two neighbors X and Y, I look at the ratio of their probabilities, and then I pass that through a function g, which satisfies this. So one thing you can take for g is just the square root, right? So it's saying broadly that you prefer to go to locations which have higher probabilities, but you don't sort of prefer them too greedily. It's a bit more careful. Okay, and so this construction was done in the work of Giacomo Zanella in 2019. And he didn't formulate it as a jump process per se, but the idea is very much there. The jump rates fall out of his work. And okay, so why reversible? Because it makes things tractable. It makes it very easy to check that you have the right invariant measure. And why do this? Because it is faster. So they compare to things like random walk samplers and so on. What is sort of clear in some sense is that, if the state of the chain, it will mix faster because you're looking at every neighbor at every step and then picking amongst them. So you're using more information. What is not obvious is that this will make you mix faster in real time, but in fact, this is also true. Okay, so you get a better practical algorithm using this reversible Markov jump process. Okay, so what I want to do to build on this, and what Jacob and I worked on, was to make this non-reversible. And so the motivation behind using a non-reversible process is essentially that you can hopefully get better mixing. So broadly speaking, a process which is reversible has no sense of direction. The sort of detailed balance condition says if you have any two neighbors, you're as likely to be passing from x to y as from y to x at stationarity. Whereas a non-reversible process can add in some notion of momentum, which will prevent it from backtracking. And usually this is done by explicitly introducing some auxiliary variable, which behaves like a momentum or a velocity or a direction in some way. And so that's what we want to do. So the idea is, empirically and from a bunch of concrete algorithmic examples, we know that this can help convergence, and we want to see how we can do this for discrete spaces. Okay, so what we're going to do is assume some sort of structure on our space, which makes it a bit more transparent how to construct such a process. And so here we will assume that we have a space X, which is discrete, which is acted on by some group G, and we sort of distinguish a generating set for that group, which is going to be like a basis for the group morally. So the idea is to view the generators as being like velocities, and then from that we have a natural auxiliary variable, and we can build a process which is sort of, okay, I have a position and a velocity, I'm going to follow that velocity for a while until it stops being useful. So a key distinction which we make in the paper is whether your set of generators is high order or low order. So the standard example would be if you're on sort of a lattice, like the integers, your generators, you can keep applying them and you just keep going, right? And so there is some incentive to apply them repeatedly. Whereas on something like, the integers mod 2, if you apply the generator once, you end up back, if you apply it twice, you end up back where you started. And so there's an incentive actually to not reuse them. Okay, and in this talk, I'll basically focus exclusively on the low order generators, because the high order ones are sort of a lot more like the Euclidean case, and you can kind of build the intuition already. Whereas here it's a bit more not obvious. And it's worth saying that the properties of the generators is a feature of the space you're on, the group you've chosen, the generators you've chosen. It's not a feature of the target measure per se, but it will sort of be informed by it implicitly. Because you sort of, you have to choose what group you're using and what generators you're using, and the nature of the target will suggest that most of the time. Okay, so the sampler we sort of developed is called the taboo sampler, and it's built off what's called sort of taboo search, is a sort of way of solving constraint satisfaction problems. It's a heuristic solve, right? But the idea is essentially, if I have my position is a bunch of coordinates, if I've just changed this coordinate, I should disincentivize changing this coordinate again, because it would correspond to backtracking. Right, yeah, so we're in the case where all generators are in involution. If you have made the same move twice in a row, you would end up back where you started. And so the intuition for the process we're gonna explore the space with is, when you use a generator, you throw it away, at least for a while, right? You say, I've flipped the first coordinate, I'm gonna leave the coordinate alone for a little while until it be clear that it's necessary to use it again. So let me see, I should have. Yeah, so there's an extended variable formulation of the whole thing. So you have X is the state we're interested in. We have this vector alpha, which will essentially encode which of the generators we're allowed to use at any given time. So it's going to be plus or minus 1. And for each generator, I should say. And then we have this arrow of time variable, Tor, which is going to be plus or minus 1. And so what happens is that when Tor is equal to 1, we are allowed to use the generators such that alpha is equal to 1. When Tor is equal to minus 1, we can only use the generators such that alpha is equal to minus 1. Okay, we should have a diagram on the next slide. Right, yes. So over here, I have my big bag full of all the generators. And whilst I'm running the algorithm, it's split into the ones that I am allowed to use, so with alpha is equal to Tor, and the ones that I am not allowed to use, where alpha is equal to minus Tor. And so how the algorithm works essentially is we're at our current state X, we look into the bag of things that we're allowed to use, and based on the information, so I should emphasize the decision of the gamma we choose will depend on X. So we take our X, we look in the bag, we pick a generator to use, we apply it to X, which gives us a move to Y, which is sort of gamma applied to X. And then we take the generator and we put it in the other bag, okay? So that is the sort of intuitive process of what's happening for most of the chain. And then the additional thing that happens is if the bag of generators that we can't use becomes too appealing in some sense, if it would be much more preferable to use something in the forbidden bag, then we swap them, right? We flip Tor. So that's what happens. So yeah, this is just in words and symbols what I said before, right? The move of type 1 is a generator. So if alpha of gamma is equal to Tor, we move from x to gamma dot x, and then we flip the generator. So that's sort of putting it in the other bag. And this happens at sort of this rate I described earlier. It's sort of like a function of pi of y divided by pi of x, where y is this guy. Okay, and then the second move is the swap bags move, which essentially happens with a weight corresponding to how much more you would rather use the other bag. Okay, so I think of sort of each bag is as heavy as the rates with which you would like to make the jumps corresponding to them. And so you swap the bags if one is too heavy. Okay, so the observations we make, okay, this is the way this is constructed, it's non-reversible. You know, if you have jumped from x to gamma dot x, then you couldn't jump right back. Okay, you'd have to flip Tor to do that. And so as a result, we avoid backtracking. And so for things like spin systems and permutations and so on, we are really getting this diverse collection of moves behavior, which we were hoping for. Fortunately, or sort of by construction, we still have an algorithm which leaves pi invariant. So we get the right measure at the end of the day. We are sort of sampling correctly in the way I want it to be. And the way we prove this is by proving what's called skew reversibility. So it's sort of, instead of saying the flow from x to y and the flow from y to x are the same, there's sort of a mirrored version of that where it's, you know, the flow from x to y when Tor is equal to 1 is the same as the flow from y to x when Tor equals -1 in the sort of, you know, upside down universe. And sort of the key thing is that empirically it improves convergence, and also theoretically you can show that it does. The argument is essentially that if you average out over which direction you're going in time, you get back to the reversible algorithm, and then there is sort of general theory which says the non-reversible algorithm is better in that case. It's better not to average out like that. And yeah, just emphasize that it is exactly implemented in continuous time. There is no discretization error. There are actually no tuning parameters except at a very high level, right? So that's good. So we've sort of achieved most of what we wanted to. I've not put any plots of convergence in because I don't think that would be super interesting. Essentially, you would just see a trace plot going like, oh, it's mixing very well, which is nice, but is not that much fun for you, I suppose. Right, so some extensions we're interested in are fusing this with continuous space samplers. So it's quite rare in Bayesian stats that your posterior will just be discrete variables. If you do have discrete variables, they will be paired with something continuous a good chunk of the time. And so the idea is, okay, I'll take some continuous space sampler, like the bouncy particle sampler, for example, and this taboo sampler on the discrete variables, and maybe I have them both evolve together in continuous time. And that is sort of a nice way of trying to fuse everything. You don't want to have to alternate between updating different parts. It's very seamless to do it all at once. Right, a natural question is sort of, can we adapt the generating sets? So what I mean by this is, you know, suppose we see that it's very common to use this generator and then this generator in quick succession. It would be useful to be able to combine those into an extra generator. It's kind of like if you were playing chess and you create a piece that can make even bigger moves because you see that that's useful. And so we think this could be done adaptively in a pretty simple way, and would be quite useful. So it's nice. Yeah, dynamically interacting samplers. This is sort of a broad curiosity of mine is if I want to have, instead of one Markov chain, I want to have, you know, K particles exploring collaboratively in some way. How should they communicate information? It's not horribly difficult to work this out on continuous basis. It's a pretty new development, but it's not unboundedly complex. But on discrete spaces, I actually don't know how to do this. And still get the right invariant measure and actually improve things. So that's something I'm super curious about. And then a final thing is for continuous space samplers, if you want something to mix quickly, it is essentially, you know, very close to necessary and sufficient that the measure be log concave or log concave in the tails. You know, you have some sort of pretty strong structural assumptions there. If I'm on a discrete space, what is the right notion of, you know, being log concave? It's quite unclear. You know, in particular, if I'm trying to sample a distribution over permutations, what is a condition which makes that easy for me? And I don't know how to write one of those down. Yeah, I think I might have one or more comments. Yeah, just a final thing. So we can show that it's better in theory, and empirically it's quite a lot better in practice. It's quite nice in that it adapts to the difficulty of the problem quite gracefully. So, as a problem gets more difficult, obviously any sampler is going to get worse, but the relative benefit of using more advanced non-reversible samplers does become more pronounced. So if you have a really hard problem, you really should try to use something more advanced like our sampler. Okay, I think I'm about to stop talking. Thanks very much.
Yes. Thanks a lot, Sam. That was a very nice talk. We have time for a very quick question if someone has one. Otherwise, I was curious when you were talking, I think on slide 8, about your kind of, I think the restriction was that you're only allowed to move to neighbors. Could you relax that and allow jumps kind of to like neighbors a little bit further away as well?
Yeah, you can. I mean, so the way I would think of that is that you are changing the graph.
Yeah.
So from the theoretical point of view, it's pretty easy to do. The other thing you would want to be careful of is that doesn't create too many more neighbors. So right in our setting, we normally have n neighbors, where n is the complexity of the model in some sense. If you start looking at jump 2 neighborhoods as well, you might go up to n squared, right? And so depending on your problem, that might be affordable or not.
Yeah, thanks a lot.
Just.
Then in interest of time, we're moving on to the next speaker. Thanks a lot again, Sam.
Thanks very much, Torben.